Hello all. In this video, we'll be looking at some very basic statistical assumptions, namely stationarity, integration and cointegration, and how these three things tie together in the world of algorithmic trading. There's this very famous trading algorithm called the pairs trading algorithm, which uses this concept of cointegration. I was initially planning to make a video on pairs trading, but then I realized that I should first make a video that covers these concepts of stationarity and cointegration separately. And so without further ado, let's start with the video. Let's see what stationarity is. But before that, I should mention that I have put the link of this Jupyter notebook in this video's description, so feel free to check it out. So yeah, what is stationarity? Well, there are many definitions of stationarity, and we'll be working with the wide sense definition of it. Basically, let's say you have been given a time series, right? And the elements, and if the elements of this time series are all drawn from the same exact probability distribution, by that I mean is they're all, I mean the probability distribution has its mean and variance constant, right, not changing, then we call the time series to be stationary. For example, if you have your time series elements to be drawn randomly from a normal distribution having a constant mean and variance. Now, why is this important? Well, when you build a model, right, you're fitting to some probability distribution or underlying characteristics of the data, and we want these characteristics or the assumptions to remain the same and not change. Why? Because see, if there is some shift in the mean or standard deviation or some other parameters of this probability distribution, then there is no reason to believe that our model that we have will still hold, because the model that we are using is built on totally different regime than what we are on right now. And hence one can realize that it is very necessary for one to test for stationarity in time series analysis. Let's take a look at some examples. So first, let's import all the necessary packages that we need. So I have imported NumPy, Pandas, stats models and matplotlib.pyplot, and this function over here generates data points randomly from a normal distribution with the parameters that the user gives it. So the first element of this parameters array is the mean or mu, and the second one is the standard deviation or sigma. And then let's create a time series which is whose elements are randomly sampled from a normal distribution whose mean is 0 and standard deviation is 1. And so I've set my parameters to be 0 comma 1. We want about 100 elements in a time series, and let's call our time series A, right? And this for loop here generates data points which are sampled randomly from our normal distribution. And so when he prints the plot would get such a plot, and this plot just looks like random noise, right? Random noise whose mean is 0 and variance 1. And by definition we know that this is a stationary time series. Now let's look at how a non-stationary time series would look like. So essentially what I've done now is I have created this example where the mean of the distribution from which we are randomly sampling our points to change or to increase with respect to time. So I have set my mean to be 0.1 times t, right, which is basically linearly increasing with time, and my variance to be constant, same as before, which is 1, right. And I have plotted what our time series would look like, and as you can clearly see, the mean keeps on increasing, which is by definition, right, because we have defined our mean to linearly increase with time. And there's one very important thing, that some of our most fundamental techniques that we use are useless when we lack stationarity. And there are many statistical tests that require data to be that we test to be stationary, and one would just get garbage results if certain statistics are used on a non-stationary data set like this one. Now let's also plot the mean of the entire data points that we have here, and it's kind of obvious that the mean will be around 5, right? Now what does this tell us? Well, it tells us absolutely nothing, right? Because this computed mean of the entire data points is just useless for forecasting any future states, because this mean just tells us nothing except for the fact that how the middle portion of our time series would look like. And this just clearly tells you that non-stationarity can just screw up with your analysis. There's one solution to this problem though, I mean, to analyze a non-stationary time series, which is that you could use a moving window average, which will smoothen out a curve a little bit, but it will introduce a problem. The problem is lag, and this lag is basically proportional to how long your average window is. And basically the information that you get will be a lot later than when you actually want it. Now let's look at some tests for stationarity. One of the most popular ones being augmented Dickey Fuller test. We won't go into the math of how do you test for stationarity, and we'll just call functions and quickly find out what its p-value is, and define a cutoff, and then figure out whether the you know data set given to you is stationary or not. So I've defined a function check for stationarity, and I've set a cutoff to be 0.01, and I've used this add Fuller function from the module that we have called above. So your if your p-val is less than the cutoff, then it's likely that your time series is stationary, and if it is above the cutoff, then it is likely it's not stationary, right? So I have checked for stationarity of time series A and B. The time series A was just having a constant mean of 0, and time series B was having its mean linearly increase with time. And as you can see, the results clearly show that time series A has a p-value of 2.5 into 10 power minus 4, and which is likely stationary, and the time series B has a p-value of 0.9, which is obviously bigger than 0.01, and so our time series B is likely non-stationary. Now let's go to a more subtle trend, wherein the time series given to you would look like it is stationary, but by definition or in actuality it isn't, and it's possible that your tests also give you the wrong answer. So let's go over this example wherein I set my mean to vary periodically. Let's define our mean to be sine of t, right? And let's try to get a time series. And after doing so, you get this plot which is very similar, this time series very similar to your time series A, because this just looks like noise with mean 0 and variance 1. But I mean, this is how it just looks like, but by definition we know it is not. We know it is a non-stationary time series. As we can see, it is clearly dangerous to just look at graphs and figure out whether the time series given to you is stationary or not. We should in fact look at graphs and tell us whether the time series is non-stationary, because it is quite obvious that when you notice a characteristic of this graph to not be of a stationary time series, then you can clearly conclude that this time series is non-stationary. And looking from this graph that we have here, this time series C, one might say it's stationary, but in definition it actually isn't. Let's also check this from using our statistical tests. So let's call the function check for stationarity on our time series C, and we get our p-value to be 0.67, which is obviously bigger than 0.01, and hence our time series is likely to be non-stationary. And as you can see that most often than not, this statistical hypothesis test is going to give you the right answer. And it's quite okay to put some faith in it, especially when we don't understand the underlying relationship, especially when it's as subtle as this time series C that we just plotted here. Now let's move on to the concept of integrated of order n, right? And when n is 0, we call it to be integrated of order 0 or just I0, and it just primarily refers to the stationary time series. So we had plotted our time series A, which was randomly sampled from a normal distribution of mean 0 and variance 1, right? We can just call that stationary time series A to basically be I0, and one can just inductively build up orders of integration. So I1 basically would mean that you're cumulatively summing up the I0 time series. I2 would be just cumulatively summing up the I1 time series, and so on. So let us see how your I1 time series would look for time series A, right? So I just wrote the code A1 equals to np.come sum A, and after plotting it, you see that we get our plot to be a lot smoother, and this I1 plot for the time series A starts looking more like a price process. And this is kind of how the financial time series tie into this idea, right? And if one wants to plot the I2 for this I1, or basically cumulatively summing up the A1 time series, which is I1, right, you get this plot here, which is a lot more smoother, and one could just keep on going until the person gets the integrated of order n time series. Now let's look at how do you break down orders of integration, or basically to go in the reverse direction. Well, one would need to take the inverse of the cumulative sum which we have taken earlier, right? Which is basically the delta or the itemized difference. And so we introduced this new operator called L, which is just the lag operator, and it fetches the second to last element in the time series. So basically, it just fetches the element before that particular element, right? And so by definition, LK will just fetch the kth to the last element, right? And I mean, when somebody just writes it mathematically, it would just be L xt is equals to xt minus 1. And so for finding the difference, you would just do 1 minus L times xt, which would give us xt minus 1. And so if a series xt is I1, then when you apply this operation 1 minus L times xt, you would get I0. And by definition, I0 is a stationary series, right? And let's say you have an integrated of order n time series, and we would have to take the first order differences n times to get back your I0 time series. So let's just check this out with some real life data. I have imported the Y Finance library and I'm using the Apple stock, right? So I'm downloading Apple stocks from the 1st Jan of last year to till the 1st Jan of this year, right? And I'm using the closing prices, and I'm storing the time series in the variable x and checking for a stationary. And as you can see that I'm also plotting the time series here. You can clearly see that the time series is not at all stationary, and that is what our test tells us as well. It gives us a p-value of 0.81, and which is obviously which obviously tells us that that the time series is non-stationary. Okay, now let's take the delta of this series, which would give us the additive returns, and check if this delta is stationary or not. So we'll just write this line of code, x1 equals to x dot diff, and take from the second element onwards. We're doing so because the first element of our x1 would just be NA, because this element comes by taking differences of two elements, right? Two consecutive elements, and since there is no element before the first one, it would just be NA. And yeah, so this piece of code is just making my plot look more beautiful, more legible, right? And when you plot your x1, when you plot the delta of the series, then you get this random noise which clearly looks stationary, right? And that is what your test tells you as well. It gives you a p-value of 5.2 into 10 power minus 4, and which tells me that it is likely stationary. And let's also check for the multiplicative returns. So we'll just do x1 equals to x dot pct change, percentage change, and again take from the second element onwards for the same reason, right? And then let's look at how it would look, and it clearly looks the same, right? The plot clearly looks like a stationary, and that's what our test tells as well, because it gives me a p-value of 4.45 into the power minus 15. And so one can clearly conclude that your additive returns or your multiplicative returns are stationary, or just I of 0, and your original time series, your Apple's closing prices, is I of 1, right? Integrated of order 1. Now we have tested and determined that at some point in the past the return series was stationary, or obviously the price series is I of 1, but it's not necessarily going to be true in the future. And so you need to constantly keep checking whether our base assumptions hold while making the model, because things can just abruptly change, especially when we're not expecting them to. As a fact, we generally assume that the returns are stationary, which is the base assumption of a lot of financial mathematics, because it's rooted in the idea that prices are log normally distributed, and so the return series that you get will be normally distributed or stationary. Finally, let's go over to co-integration. Let's say you have a set of time series x1 till xk, right? Then one can just construct a linear combination of these time series inside this set to give you time series y. And so obviously y is just going to be summation bi xi, right? And by definition of co-integration, we need the time series inside this set to be I of 1. And if for some linear combination we get that linear combination to be I0, then we call this set to be co-integrated, this set of time series x1 till xk to be co-integrated. Now when we have real life data and we're trying to build a model on it, we don't have much info to use, and using statistical methods there's very less that one can get to know and use it for analysis. For example, if the person has a stationary time series, then all he knows are the parameters and some tests to figure out what sort of distribution that the data belongs from. But if we get to know that we have a set of co-integrated time series, then it indicates that there is a subtle relationship between the time series involved. So, like, if you know that if you have, your x1 and x2 to be co-integrated, then there is some driving under factor between x1 and x2 that could give us a little more piece of information that could be helpful in our analysis. So now let's look at how a co-integrated set of time series would look like. So I have generated a stationary time series x1 whose elements are randomly sampled from a normal distribution whose parameters are 0, 1, mean 0, variance 1. And then I create the I1 time series of this x1, right? I just cumulatively sum the elements of x1, and then I just replace or modify our original variable x1, right? And then I create a new time series x2, which is this x1 plus some noise. This noise is also randomly sampled from the normal distribution 0, 1, right? And then I just look at how x1 and x2 look like. As you can see, like, they're very close to each other. x2 just differs from x1 because of the noise that we have, right? And we know by definition that x1 is I1 because it is built by cumulatively summing up elements from an I0, which is, or a stationary time series, and it's obvious that x2 will be as well. For just completeness sake, let's just double check. So obviously we could, I'm trying to prove that my x2 is I1, right? So let me just prove that the x2 dot difference, or the first order difference is going to be stationary. So I just write z is equals to x2 dot diff and take elements from the second element, and after checking for stationary I get my p value to be very small, 3.6 into 10 to the power minus 16, and so it is likely to be stationary, and hence our x2 is also I1. Now, by construction, we obviously know what linear combination of x1 and x2 will give us our I0, right? It's just going to be x2 minus x1 because x2 is just x1 plus some noise, right? So this noise is I0, and to get your noise, we'll just do x2 minus x1. And so let us, call our x2 minus x1 to be z and check for its stationarity. So this is how z would look like, and it's clearly, it clearly looks like noise which is randomly sampled from a normal distribution from 0, whose mean is 0 and variance is 1. And after checking for stationarity, we get our p value to be 1.3 into 10 to the power minus 16, which indicates that the noise, or our z, is likely to be stationary. And this proves that x1 and x2 are co-integrated. Now real life data is now going to be as nice as the simulated data that we had here, right? We're now going to know what specific combination, what specific linear combination is going to give us our I0 time series, our stationary time series. So we need to figure out a tool that will be able to give us our coefficients of the linear combination. And so it's common that when we have pairs of time series, like we had x1 x2 here, right? It's a common way to estimate the coefficients using the simple tool of linear regression. And so you should be able to figure out what beta is in this x2 is equals to beta times x1 plus alpha plus epsilon. Here epsilon is noise and alpha is just like a translating factor to noise. I am trying to put my epsilon to have mean 0. And so this combination x2 minus beta x1 which will give me alpha plus epsilon, should essentially be stationary. Let's try this out on some real data. We would use EWA and EWC, which are the Australian and Canadian stock market ETFs, which are often used in pair trading, and download data from 1st Jan 2016 till 1st Jan 2017 and use closing prices. We just plot how both the time series looks like and then calculate the linear regression between them and see whether the beta that we get allows us to construct the linear combination that's I0. So this is just the code for the least squares regression, and we get our beta for EWA to be 1.74223. We then use this beta to construct our linear combination and try to figure out whether our linear combination is I0. So we use z is equals to x2 minus b times x1 and then plot how our z would look like. So this is how z looks like, and just by looking at it, one cannot obviously conclude that it is stationary because it's not very obvious, but one could just probably guess that it is stationary because it has a constant mean and variance, or at least seems to have a constant mean and variance. One could just check whether our time series z is stationary or not by using the statistical test that we had discussed earlier. So just by calling the function check for stationarity, one could just find what the p-value is. The p-value turns out to be 0.00158, which is below the cutoff of 0.01 and indicates that our time series Z is stationary, and hence our linear combination is I0, and so we can conclude that during this period of 2016 and 2017 our EWA and EWC were likely to be co-integrated. Now, similar to the issue with stationarity, this is only a forecast, and we can be sure that the two stocks which were co-integrated in the past continue to still be co-integrated in the future, especially when we do not have a lot of things under our control. Generally, when we look for co-integrated stocks, we look within some universe where we think there is going to be some underlying relationship governing it. So we look at stocks within the same industry or in closely related industries like individual shipping companies or manufacturer and supplier of steel, and check whether they are co-integrated. But if there is some sort of regime change, example if one of the companies gets some new management and decides to switch what they're doing, then a pair that was previously co-integrated may now not remain co-integrated, and so we might run into issues if we are trying to place bets on co-integration. Finally, we don't have to necessarily deal with the process of constructing a linear regression, finding our beta and then testing whether this linear combination is stationary or not. We just have a built-in test for this co-integration, and it can just be found out by using this line of code coint x1, x2, and our p-value can be found out here. Turns out to be it is 0.00617. Thank you for making it till here, guys. If you found this video to be quite educative and insightful, don't forget to subscribe to my channel to stay updated with the content that I post. Also, I've put the link of this Jupyter notebook in the description, so feel free to check it out. Thank you.